In this video, we present our interpretation of quantum mechanics, the Glassboro interpretation. We seek for a theory that has the key feature of the de Broglie-Bohm theory but does not have the guiding equation. We substitute the guiding equation for the conservation laws.
Our candidate for the wave component is the zero-point field. The zero-point field is a ground state of a quantum field, and for certain physical effects, it offers the only explanation. There are many properties of zero-point fields. Here are a few.
Zero-point fields exist even in the absence of particles and fill all of space with minimal energy. There is a zero-point field at every point in space for every allowed energy momentum state and for every type of elementary particle. Zero-point fields can be static or dynamic.
They propagate in a vacuum according to the wave equation and boundary conditions. When a particle occupies a zero-point field, the field does not change or get distorted. A zero-point field does not collapse once a particle vacates it. Zero-point fields can be generated by sources. They do not propagate noticeable amounts of energy momentum.
There is physical evidence for the existence of zero-point fields. They are the main component of the cosmological constant or dark energy. Zero-point fields are also evident by Casimir's effect and Lamb's shift in hydrogen. To demonstrate what zero-point fields are, we have three examples: Casimir effect, a proton at rest, and dynamic zero-point fields.
Physicist Hendrik Casimir predicted that the vacuum contains a huge number of zero-point fields. The Casimir effect is a small attractive force that acts between two close, parallel, uncharged conducting plates. It is due to zero-point electromagnetic fields.
Two plates or mirrors are facing each other in a vacuum. The mirrors are separated from each other. Electromagnetic zero-point fields obey boundary conditions. There must be nodes at the mirrors. Thus, only wavelengths that are multiples of the separation are allowed within the mirrors. Outside the mirrors, the boundary conditions are more relaxed. Thus, more zero-point fields are present. The excess of zero-point fields outside compared with inside the plates results in a small force drawing them together.
Casimir force can be calculated by the equation shown. Here, h is Planck's constant, c is the speed of light, and L being the distance between the two plates. Now we go to the second example, a proton at rest in a vacuum.
The positive charge of the proton induces the vacuum to form a hydrogen-like zero-point field. There will be hydrogen-like zero-point fields for negatively charged electrons, muons, quarks, etc., even if none of these particles are actually present. If a free electron comes near the proton, it could take a hydrogen-like zero-point field. The plane wave previously occupied by the electron does not collapse, but remains in the vacuum as an empty zero-point field plane wave.
Our third example is dynamic zero-point fields. For decades, theorists have predicted that by shaking zero-point electromagnetic fields present in vacuum, real photons could be generated. This could be done as follows. At the surface of a mirror, the zero-point field has a node. Thus, if the mirror is shaken, then the node shakes, making the field attached to them also shake. Since the field obeys Maxwell's equations, it would start to propagate, carrying photons with it.
Using the current knowledge known about zero-point fields, we're presenting our answer to the paradoxes presented before with the Glassboro interpretation of quantum mechanics. To begin, our requirements are for it to be sensible, to be based on conservation laws, to be consistent with the math of quantum mechanics, and to be consistent with experimental evidence.
Our theory declares that the particle, carrier of the conserved quantities, is a point-like object. The wave function for the particle is a zero-point field. In essence, the wave-particle duality paradoxes are solved the same way as in Bohmian mechanics. However, we use the conservation laws rather than the guiding equation to define particle movement.
In Bohmian mechanics, the wave function drives the particle according to the guiding equation. However, in the Glassboro interpretation, the particle is driven by regular forces, such as electromagnetic forces, weak and strong forces, or by a subquantum force of the same nature as the force that keeps two neutral fermions from occupying the same state. Therefore, the zero-point field or wave function represents a force field that drives a particle only when the conservation laws are met. If we look back to the paradox from the last video in which polarization of two distant entangled photons were measured, it was a mystery how information to conserve angular momentum must travel faster than the speed of light. However, A zero-point field carries neither energy nor momentum, allowing information about the conservation law travel at any speed.
It must be stated that the Glassboro interpretation is probabilistic. For instance, if two possibilities that obey conservation laws are equally likely, then the particle randomly takes one.
In the Glassboro interpretation, there is no collapse of the wave function. A particle just vacates a zero-point field and occupies another. The empty zero-point field does not collapse.
Here, the physical reality of the vacuum along with zero-point fields are emphasized. We encourage the study of the vacuum as a physical structure. If a vacuum is a physical structure, the gravitational forces would have more to do with the changes in its overall structure, rather than with gravitons that transmit the force of gravity. This view is compatible with Einstein's theory of gravity. Thus, this theory could redirect the study of quantum gravity.